Something strange is moving through our solar system right now, and it's not acting like anything we've seen before. It's not just drifting along or spinning out of control. It's moving with intent, with a kind of accuracy that makes even the most experienced astronomers stop talking and just stare at the data. They're calling it 3IATLAS, an interstellar object that showed up in our neighborhood in 2025. At first, it looked like just another comet, a frozen lump from some distant star system, passing through on its way to nowhere in particular. That's what the early press releases said anyway. But the truth is, nobody mentioned what really matters. This thing isn't slowing down, it's not behaving like any comet we know, and it's headed for a very specific spot in space, with a precision that honestly shouldn't be possible. Here's the target: Jupiter's Hill radius. That's the zone where Jupiter's gravity takes over from the sun's, a kind of sweet spot where moons gather and spacecraft aim when they want a stable orbit. 3IATLAS is threading right through that, not just roughly, but with the kind of accuracy you'd expect from a mission planned by NASA. The intercept point, exactly 53.445 million kilometers from Jupiter's center, give or take just 60,000 kilometers. To put that in perspective, imagine tossing a dart from New York and hitting the bulls in Los Angeles. Oh, and both cities are moving. And you threw the dart 7 years ago. That's how precise this is. Nature doesn't work like this. It just doesn't. Space is a mess. Comets tumble, solar wind knocks them around, gravity from planets pulls them off course, and their own jets of gas spin them unpredictably. Their paths are always shifting. But 3IATLAS moves like it already knows the route. Like someone mapped this journey out ages ago. That's the detail that's keeping scientists up at night. Because if this thing is natural, it's breaking every rule in the book. And if it's not natural, then we've got some really different questions to ask about what's happening out there. So how did we find it? July 1st, 2025. The Atlas Survey Network, just a bunch of telescopes in Chile, scanning the sky for anything that might smack into Earth, spotted a faint smudge against the stars. At first, it was just another blip in their endless database of rocks and comets. The computers logged it, ran some quick calculations, and moved on. Nothing special. But when real live astronomers checked the data later that week, something stood out. The path was just wrong. Not a math error, just a trajectory that didn't fit anything you'd expect from objects in our solar system. Most things out here orbit the sun in neat ellipses, looping around endlessly, locked in by gravity. But this object, it was on a hyperbolic path, moving too fast to be captured, curving through the solar system like it just dropped in for a visit. When astronomers traced its path backward, the numbers all pointed to the same conclusion. This thing isn't from around here. It's interstellar, only the third one we've ever confirmed, after Oumuamua in 2017 and 2I/Borisov in 2019. That label 3I/Atlas pretty much sums it up in astronomer speak. 3I means it's the third interstellar object we've found, and Atlas is the survey that spotted it first. The moment news broke, any observatory that could see it jumped in. Hubble swung into action. The James Webb Space Telescope tuned its infrared eyes on it. Ground-based telescopes all over the world planned out their observations. Even the Mars orbiters, solar probes like Stariway and SOHO, and spacecraft scattered through the inner solar system started gathering data. It turned into a huge all-hands-on-deck observation event, the kind you only get when something truly rare shows up near home. Right away, early images made it look a lot like a comet. A bright core, wrapped in a fuzzy coma, just what you'd expect when sunlight hits a ball of ice and gas. Spectrographs picked up water vapor, carbon dioxide, carbon monoxide, and the usual dust. All the classic comet ingredients showed up. The thing even started growing a tail. Sunlight and solar wind pushed gas and dust away, stretching it out behind. So far, so comet-like. But even then, the data didn't sit quite right. For starters, nobody could pin down its size. Some estimates put the nucleus at just 440 meters across. Others said 5.6 kilometers. That's a massive difference. Are we looking at something the size of an office tower or a small mountain? The problem is you're guessing, trying to separate the solid core from the haze of gas and dust around it. Every guess about what it's made of, how shiny it is, or how active it's been can swing the numbers wildly. For something this important, that uncertainty drives scientists nuts. Then things got weirder. Webb's infrared data showed the coma wasn't mainly water vapor, like almost every comet from our solar system. Instead, carbon dioxide dominated. The ratio of carbon dioxide to water turned out to be one of the highest ever measured. This puts 3IATLAS way outside the usual range for local objects. Sure, it still had water ice, carbon monoxide, carbonyl sulfide, and organics, but carbon dioxide was running the show. That's not what you'd expect. Solar system comets are usually packed with water ice. They formed where that was easy to find. But this thing grew up somewhere else, around another star, in conditions we can only imagine. Ultraviolet telescopes piled on more surprises. Even when it was more than 3 times farther from the sun than Earth is, 3IATLAS kept pumping out water vapor. Telescopes picked up hydroxyl emissions, basically signs that sunlight was breaking water molecules apart. That just doesn't happen with most comets at those distances. It means either this comet's ice turns to gas at lower temperatures, or something about its insides makes it weirdly active, even when it's supposed to be frozen and quiet. Whatever the reason, it's not following the rules. But here's the part that really stops you. It's not just the chemistry or the activity, it's where this thing is headed. If you run the trajectory forward, look at where 3IATLAS should go in the months ahead, the path is just off. The numbers say it's heading straight for Jupiter's Hill radius, like, almost exactly. That kind of precision doesn't happen by accident, not for a random visitor drifting through space. And that's the detail that takes this from a scientific oddity to something that feels almost unsettling. Jupiter's Hill radius stretches about 53 million kilometers out from its center. That's the invisible line where Jupiter's gravity wins out over the sun's pull. Inside this bubble, Jupiter's grip is strongest, perfect for moons and satellites to hang around. This is where natural satellites tend to form, since the laws of physics actually make it easier. And when we send spacecraft to study Jupiter, this is the zone we aim for. Once you're inside, you don't have to battle the sun's gravity as much. You can settle into a stable orbit, almost like dropping anchor in a sheltered bay. Now look at the numbers for 3IATLAS. The intercept point sits at 53.445 million kilometers from Jupiter's center, give or take 60,000 kilometers. Seriously, read that again. That's not just close. That's not even in the ballpark. That's threading a needle, except the needle's floating out in deep space and you're tossing the thread from hundreds of millions of kilometers away. The margin for error is tiny, a few thousand kilometers, but the scale is so huge it almost feels impossible. Yet, this is the kind of precision you see in spacecraft missions, where teams spend years crunching numbers, mapping out every gravitational nudge, every tiny twist and turn, just to land in the right spot. Let's clear up something about targeting versus close approach. Lots of stuff drifts near planets. That's normal space is packed with asteroids and comets zigzagging on wild paths, and sometimes they just happen to swing by Jupiter or Saturn. The solar system is huge, and over millions of years, random flybys happen. But there's a huge difference between a random close call and actually hitting a specific gravitational boundary, with a margin of error that's just a sliver of a percent. Pulling that off takes either impossible luck or someone steering the ship. And 3IATLAS isn't just getting in the neighborhood of Jupiter's Hill radius, it's landing right on the boundary, almost surgically. Independent astronomers, real researchers, not just internet sleuths, have been running their own numbers with the data anyone can access. And they all keep landing on the same answer. The path is just too sharp, too spot-on, too intentional. These aren't wild conspiracy theorists squinting at blurry images. These are credible people with the same orbital data as NASA, and they're not comfortable with what they're seeing. Some are even calling it an insertion maneuver, the kind of move you'd expect from a guided spacecraft, not a random comet wandering in from interstellar space. Officially, NASA and other space agencies are sticking with the "it's just a comet" story. The database still lists 3IATLAS as a natural visitor from beyond the solar system. And to be fair, there's no clear-cut proof of anything artificial. No weird radio signals, no obvious signs of engines, nothing in the images that screams built by someone. On paper, it could just be a freakishly lucky comet that happens to be flying a perfect probe's course. But here's the thing, that explanation gets harder to swallow every day. The path isn't just precise now, it's been getting more precise as time goes on. Take perihelion, October 30th, 2025. That's when 3IATLAS got closest to the Sun, about 1.4 astronomical units away, just inside Mars's orbit. At that distance, any normal comet would heat up, start spewing gas, and get much brighter. And that's exactly what happened. Outgassing, a glowing coma, all the classic signs of a comet waking up in the sun's heat. But then things went sideways. After perihelion, most comets get a little wild. Outgassing kicks them around, makes their paths wobble. Not this one. 3IATLAS actually tightened up its trajectory. Its path toward Jupiter's Hill radius got even sharper, as if something, or someone, was making small course corrections along the way. That's just not how sublimating ice acts. When a comet starts venting gas, the jets shoot off in all sorts of directions, wherever the sun's heating the surface, and depending on how the nucleus spins, it's messy. You get wobbles, sudden tumbles, weird accelerations. All this chaos makes it tough to predict where the comet's headed in the long run. You can get a rough idea, but the details, forget it. But then there's 3IATLAS. After swinging around the sun, instead of getting more unpredictable, its path actually tightened up. The route toward Jupiter's Hill radius got sharper, not sloppier. It's like someone dialed in the precision just when things should have been at their messiest. That's the kind of thing that makes astronomers uneasy. There's one moment that really sticks out for everyone watching this thing. A stretch of time when, honestly, something happened and nobody's sure how. The timing is just too on the nose to ignore. Right at perihelion, when 3IATLAS was closest to the sun, the comet slipped behind the sun from our point of view on Earth. That's called solar conjunction, a built-in blackout. The sun's glare drowns out telescopes, radio signals get lost in solar noise, and for about 2 days we can't track the comet at all. When 3IATLAS finally popped back into view, things were different. Scientists call it a non-gravitational acceleration event. Basically, something gave the object a nudge that gravity alone can't explain. Its speed ticked up a bit, but the real kicker, its direction changed in exactly the way needed to fine-tune its approach to Jupiter's Hill radius. Not just roughly in the right direction, right on the nose. The kind of course adjustment you'd make if you wanted to hit a bullseye. The usual story is simple and makes sense. Comets are dirty snowballs, ice and rock mixed together. Get them near the sun and the ice turns straight to gas. The jets this creates can push the comet off its path, making it speed up or slow down in ways gravity can't explain. We've seen this happen over and over with comets. So when 3IATLAS sped up after perihelion, everyone figured, solar heating, outgassing jets, a little nudge. Mystery solved. Move along. But that's where things get weird. Outgassing is chaotic by nature. You've got ice hidden in odd spots, the shape's lumpy, and as the comet spins, different areas heat up and vent gas. The result? Tumbling, spinning, unpredictable motion. Comets don't fly straight after perihelion. They stagger, wobble, and make life impossible for anyone trying to predict exactly where they'll be later on. Every comet tracker knows. After perihelion, all bets are off. Yet 3IATLAS doesn't look like other comets. Its coma, the cloud of gas and dust around it, shows up as perfectly symmetrical in telescope images. No wild jets, no bright rotating patches flaring up and then fading as the nucleus spins. Just a smooth, steady halo, almost too uniform to be real. For astronomers used to seeing lopsided, patchy comas with obvious jet structures, this one is just strange. It looks more like something you'd get from a perfectly round ball of ice, spinning slowly so the sun hits everything evenly. But real comets aren't like that. They're battered, lumpy, scarred by impacts and cracked by heat. They look the way you'd expect after millions of years of cosmic abuse, not like this. What really stands out is the direction of the acceleration. When scientists mapped out exactly which way the object got pushed, the vector pointed right where it needed to, tightening the approach straight toward Jupiter's Hill radius. Not just some random direction, like you'd expect if a gas jet fired off a spinning, tumbling surface. Not a messy, complicated vector you'd have to wrestle with in a simulation. No, it pointed exactly where it should if someone had done the math, figured out the perfect correction, and hit the burn right on the mark. Nature doesn't usually care about orbital mechanics. Gas jets from melting ice do aim themselves. They just push whichever way, and the object's path gets weird and sloppy. Some astronomers have tried to explain it by saying maybe 3IATLAS has an odd internal structure. Maybe there's a lopsided stash of ice on one side, and when the sun hits it, you get a stronger push in that direction. Maybe. Comets are weird, and their insides are layered and patchy. We don't know exactly what each one looks like under the hood, but even if you buy that, you still have to swallow the fact that this one lucky push happened to be in the perfect direction, with the perfect strength, at the perfect moment to send the comet right where it needed to go. Sure, you can pile up coincidences like that, but after a while, it starts to feel less like you're explaining the facts and more like you're just trying to explain them away. And then there's the timing. The acceleration happened smack in the middle of the telemetry blackout, those 40 to 60 hours where tracking was impossible. Not before conjunction, when we could have seen everything live and measured the outgassing as it happened. Not after, when the comet was out of the sun's glare and we could check every detail. Right in the middle of the blind spot, no way to watch, no way to verify. Skeptics are quick to point out that this fits a natural story too. Perihelion is when comets get the most active, and perihelion lines up with conjunction just because of how the orbits work. The sun blocks our view because the comet's closest to the sun. Nothing fishy about that. That's just physics. But honestly, if you were building a probe and you needed to make a course change without anyone noticing, you'd pick this moment too. You'd wait for perihelion, when the sun's energy is at its peak to power your systems. You'd wait for conjunction, when telescopes on Earth can't keep a close eye on you. And if your engines happen to spit out gas that look just like comet outgassing, all the better. That's perfect cover. The sun gives you both the energy to act and the camouflage to hide it. Whether you're a natural comet or something else, this is the ideal window for a maneuver. After conjunction, after the burst of acceleration, 3IATLAS entered what some scientists are now calling the corridor. It's a narrow path in space, shaped by gravity and orbital mechanics that leads straight to the Hill radius. Once you're in, with that exact speed and direction, you're basically locked onto the route. A few little nudges from other planets might tweak the path, but you're committed now. 3IATLAS is deep in the corridor, moving steadily toward its appointment with Jupiter's gravitational edge. Nobody really knows if that object wandered into the corridor by luck or if something guided it on purpose. Did a random puff of gas just happen to nudge it onto the one path, out of billions, that lands it right at the Hill radius? Or did something out there make a subtle adjustment, right when we weren't watching close enough to catch it? The thing is, the numbers back up both ideas, and that's what keeps this argument alive. Scientists are staring at the same data, the same telescope images, running the same equations, and somehow ending up on opposite sides. The line between what's natural and what's artificial is razor-thin here. Sure, comet outgassing can give you a push in one direction. The timing of perihelion and conjunction, the close passes and alignments, that's all set by gravity and orbital mechanics, not intention. But the crazy accuracy, the smoothness, the almost purposeful feel of this thing's path, it's right at the edge of what nature can explain with a straight face. Say this was a course correction. Say 3IATLAS used its close pass by the sun to sneak in a controlled burn. Now we're looking at something that understands orbital mechanics at a level that would make our best engineers sweat. Something that knows how to harness sunlight for power or propulsion, maybe. It would have had to plan this move before it even got near our solar system, crunch the numbers, time the thrust perfectly to hit the mark. Maybe it even picked a way of moving that looks just like natural comet activity, so we'd never know for sure if it was an accident or a plan. That kind of sophistication, that's unsettling. It means we're not just being visited. Something is approaching us with strategy, with patience, and with a strong desire to stay off our radar until it's ready. It means there's thought behind it, real planning, real execution. Intelligence that works on timescales and distances way beyond anything we're used to. And the worst part, we might not even be the goal. We're not the destination. We're just another stop on the way to somewhere that actually matters. Now, let's talk about what didn't happen when 3IATLAS zipped by Earth, because sometimes what's missing is more interesting than what's there. It passed close enough that any probe with even basic sensors could have scooped up all kinds of info about us. Our atmosphere, our radio signals, our heat signatures. If you wanted a quick scan of a technological civilization, this was a golden chance. But 3IATLAS, nothing, not a twitch, no mid-course tweaks, no sign it turned any cameras or sensors our way, no heat surges that hint at equipment powering up. When we pinged it with radar, nothing weird bounced back. Its brightness and spectrum didn't change, just what you'd expect from a boring old comet. From an engineering point of view, it only makes sense if Earth simply wasn't on its to-do list. Like if you're driving from New York to LA, you don't pull off in every random town unless you have a reason. Maybe you glance out the window, but you don't stop unless something catches your eye. That's what 3IATLAS did. It blew right past us without even slowing down. And that total indifference. It says something big about where we stand in the universe. Whatever this thing is after, it isn't us. We're just another yellow star with a handful of rocks spinning around it, not even worth the energy for a quick look. The sting of that, honestly, is hard to shake. We're used to thinking we matter, that we're the main characters. When we picture aliens, we imagine them noticing us, being curious, wanting to talk or invade or at least take notes. But maybe 3IATLAS is here to teach us a different lesson. What if we're not special? What if something from another star system cruised right by, didn't even blink and kept going? Because to it, we're nothing but scenery. If you're looking at this from a strategic angle, Jupiter is the obvious spot to build infrastructure if you're an advanced civilization sending probes out to other stars. Not Earth, not Mars, Jupiter. The reasons have nothing to do with life or habitability. It all comes down to energy and location. Jupiter's magnetosphere, it's a monster. The biggest, most powerful magnetic field in the solar system. Earth's looks tiny compared to it. And if you know how to tap into electromagnetic energy, Jupiter becomes this cosmic generator, giving you free power on a scale that makes even the wildest sci-fi megastructures seem boring. You could keep entire fleets of autonomous probes running more or less forever, just by harvesting what Jupiter throws off every second. Then there's orbital stability. The hill radius isn't just some boring math line, it's a parking zone. Stuff parked here can just hang out in stable orbits for centuries, even millennia, with barely any course corrections. You could leave a satellite or a monitoring station in that sweet spot and let Jupiter's gravity handle the rest. No fuel burned, no fiddly adjustments, no constant babysitting. For anything meant to watch a star system for the long haul, this is prime real estate. It's like the difference between constantly fixing up a rental and just owning a house that takes care of itself. And the view. For surveillance, Jupiter's position is unbeatable. You're far enough out to get the whole inner solar system in one shot. Earth, Mars, Venus, Mercury, they're all visible, all trackable from a single vantage point. Radio signals from Earth would hit your equipment nonstop. A constant stream of TV, radar, satellite pings, all of it flying out at light speed. You'd see everything happening in the warm, rocky inner orbits where life and chemistry get interesting. Meanwhile, you're sitting in a radiation-blasted zone where nothing biological would last long, so no chance some curious organic creatures are going to stumble across your gear. All of this adds up to a conclusion people find even creepier than the idea of aliens being hostile. 3IATLAS might not be here for us at all. We could just be background noise in a much bigger, longer mission to set up infrastructure. Picture it from the perspective of whoever sent this thing. You don't send a probe to make friends with whatever life might be crawling around on the local planets. You send it to build a permanent outpost, to gather data, act as a relay, set up a base that can run on its own for thousands or millions of years, collecting info and beaming it home. Earth. Just one more thing to keep an eye on, no more special than the asteroid belt or Saturn's moons. People love to imagine alien contact as either an invasion or a friendly visit. We picture ships coming to steal our stuff, or wise beings sharing their secrets, or maybe something in between. All of those stories start with the idea that we matter. We're either a threat, a resource, or at least interesting enough to talk to. But what 3IATLAS suggests is way more unsettling. Maybe we just don't matter that much. Our planet, our civilization, everything we've ever done, maybe it's just another blip in a galactic survey, not important enough to engage with. Just something to log and move on. We're the locals, that's all. They're not here to conquer, trade, or even say hello. They're here to build something for reasons we can't even guess. And the weirdest part, we're watching it happen almost by accident. If 3IATLAS had shown up 100 years ago, we wouldn't have spotted it. A few centuries from now, maybe we'll have the tech to catch up, maybe even send a probe of our own. But right now, in 2025, we're stuck in the middle. We can see what's going on. We can figure out where it's headed. We can argue about what it means, but that's all. We're just witnesses, watching it all unfold, unable to do a thing about it. There's this idea in interstellar exploration called the Sentinel Network. Sounds like something out of a sci-fi novel, but honestly, it's just solid engineering. The gist is, advanced civilizations don't bother sending themselves to other star systems. They send machines. Tough, smart probes built to survive the long haul, land in a new system, and here, the twist, multiply. They scatter. They build their own networks. Picture how this goes down. A big carrier craft, think the 3IATLAS if you want to get speculative, flies into a new star system loaded with dozens, maybe hundreds of smaller probes. Each one's packed with sensors, comms gear, power sources, and enough smarts to run solo for years, even centuries. The carrier heads for a stable zone, something like Jupiter's Hill radius, and then instead of blowing apart, it just calmly splits up. The probes break off, use their own thrusters, and drift into different orbits, spreading out to key points across the system. Some head for Lagrange points, those weird gravitational sweet spots where you can just park a probe and it'll stay put, barely burning any energy. Others settle into orbits around planets or moons, places where they can watch quietly for decades. A few might risk venturing closer to the star to check out rocky planets, though there's more danger there, more radiation, faster orbits, that sort of thing. The beauty here is efficiency. Instead of sending separate probes to every single star, you just send one carrier to drop a whole network at once. After the drop-off, the carrier either sticks around as a comms relay, collecting data from the probes and phoning home, or moves on to the next star system, leaving its little network behind. Over thousands, maybe millions of years, this method could fill the galaxy with these silent watchers, each one quietly recording their star system and beaming back reports to whoever built them. If a system spawns a new technological civilization, the Sentinels are already there, watching, taking notes, ready to report. Jupiter's Hill radius is just about perfect for this. That's the region where Jupiter's gravity is the boss, but inside that, you've got the Lagrange points, cosmic parking spots where gravity from Jupiter and the Sun balance out. Drop a probe at one of these and it'll just stay put, holding its place for centuries. L1 sits between Jupiter and the Sun, about 50 million kilometers from Jupiter. From there, you can keep an eye on both Jupiter and the inner solar system without ever moving. It's a prime surveillance spot, and you barely need any fuel to stay there. L2 is on the opposite side, same distance out, but always in Jupiter's shadow from the Sun's view. Perfect for hiding. Earth's telescopes can't spot anything parked there unless they're looking right at it with the perfect equipment. Put it all together, the Hill radius, the Lagrange points, and you get a three-dimensional grid of stable locations where probes can hang out for ages, no fancy maneuvers or wasted fuel needed. If you're planning for millennia, this is how you set up a network that lasts. And Jupiter has another trick up its sleeve: its magnetosphere. This thing is massive, stretching millions of kilometers and crackling with enough energy to keep electronics powered indefinitely. With the right electromagnetic harvesting tech, just souped-up versions of the coils we use on Earth, probes can tap into that energy stream. No need for nuclear power or solar panels that wear out. Just endless electromagnetic juice flowing day and night for as long as Jupiter's there. Radiation is deadly for living things, but for certain electronics, it's actually a built-in shield, if you design them right. Sure, high-energy particles can fry semiconductors, but they also help hide you. Radio signals get scrambled and swallowed up by the plasma around Jupiter, so spying with electromagnetic waves is a nightmare. Try spotting something optically, and you're up against the constant glow from auroras and energetic particles, which drowns out faint signals. If you wanted to hide electronics from early civilizations closer to the sun, Jupiter's radiation belts offer perfect cover. You get power and stealth at the same time. So, what would it look like if someone actually deployed a network like this? Let's get a little imaginative, but stick to what physics tells us is possible. Picture 3IATLAS slowly heading toward Jupiter's Hill sphere over the next few months. As it crosses into Jupiter's gravitational grip, telescopes on Earth might notice what looks like a comet breaking apart. No explosions, no drama, just the main object quietly splitting into smaller pieces. This isn't unusual, comets do it all the time. Ice and rock break apart thanks to tidal forces or heat. Nothing to see here, folks, but then something's off. The fragments don't just drift away at random. Instead, they slow down on purpose. Each piece heads off on its own, toward different points inside the Hill sphere. Some go for L1, others for L2, maybe a few dive in closer to Jupiter's big moons. They're tiny, just a few meters wide, with dark surfaces that make them almost impossible to spot once they break free of the main body. Within weeks, they scatter across the region, each settling into a stable spot, quietly watching the inner solar system. From Earth, all we'd see is a comet breaking up near Jupiter. Nothing suspicious. Happens all the time, especially around giant planets with strong gravity. What we'd miss is a whole network setting up shop right under our noses. Dozens of autonomous probes slipping into the solar system's gravitational nooks and crannies, too small and too faint to see unless you already know exactly where to look. The radiation makes it nearly impossible to spy on their electronics. By the time anyone realizes something weird has happened, the network's already running, monitoring, recording, sending data back to whoever built it. Some researchers have taken this idea and run with it, even if it's deep in the realm of speculation. They point out that Oumuamua, the first interstellar object we spotted back in 2017, moved in ways that didn't make sense. Some thought it might be a light sail or something else not powered by gravity alone. Officially, the story was that it outgassed in a weird way, but nobody really settled the debate. What if Oumuamua was a scout, a probe sent ahead to check out the solar system before the main event? What if 3IATLAS is actually a resupply ship or a network node, part of a system that's already been hiding among Jupiter's odd little moons for years? Look, none of this is proven. There's no direct evidence that earlier interstellar objects were artificial, and nobody has found a probe network around Jupiter. But the idea lines up with theories some scientists have about how interstellar exploration might work. You don't just swing by and leave. You set up shop. You build infrastructure that can watch and report for ages. And you do it quietly, using the environment itself to stay hidden from whatever life might be starting out on those rocky planets closer to the sun. If Sentinel theory is right, and 3IATLAS is actually here to set up a monitoring network, then we're living through something no one has ever seen before. Think about it. An alien intelligence just shows up, staking a claim on our solar system without asking, without warning. They move in, set up permanent surveillance, and there's nothing we can do. We can't even be sure it's happening. These probes would be tiny, quiet, hiding in places we barely glance at with our telescopes. By the time we have the tech to hunt for them properly, they'll have been here for decades, listening to every radio signal, watching every rocket launch, tracking us as we bumble our way toward becoming a true spacefaring species. And here's the part I can't shake: we might never know. Not unless they want us to. If these probes are built for stealth and passive observation, they could sit in their little gravitational hideouts for centuries, invisible and silent. No signals, no obvious activity. Just cold machines, year after year, quietly gathering information and sending it home whenever a courier swings by to pick up the data. We'd all be living under surveillance and never have a clue, growing, inventing, dreaming, all under the gaze of something we can't even detect. Scientists are all over the map about this, and it's easy to see why. The real argument isn't about whether 3IATLAS is weird. Everyone agrees it is. The fight is about what we're allowed to conclude from scraps of data, and how wild we're allowed to get with our guesses when something this big lands in our lap. One camp, the more cautious astronomers, keeps saying we should stick with natural explanations unless we've got ironclad proof for something extraordinary. And honestly, comets are oddballs. Every time we get a close look, something surprises us. Remember Comet 67P? The Rosetta mission saw outgassing patterns that seemed almost artificial, until it turned out they were just weird side effects of the comet's shape and spin. These skeptics say the trajectory probably isn't as precise as it looks. Calculating orbits gets messy, especially when non-gravitational forces might be in play. Tiny errors in the early measurements can balloon out when you try to predict where something will be months or years from now. Maybe the so-called perfect approach to Jupiter's Hill radius isn't so perfect after all. Maybe it's just differences in how teams crunch the numbers, which models they trust, or how they weigh their observations. Bad data at the start means bad results at the end. What looks like a bullseye could just be a measuring glitch. They also point out that a symmetrical coma, while rare, isn't unheard of. Some comets pull it off if they're spinning slowly, or if they're almost spherical, or if the ice is spread out just right. It's not common, but it happens. And the perihelion acceleration, sure, the timing is interesting, but that's exactly when comets get rowdy. The fact that it happened during conjunction, that's just the math of orbits. It only seems suspicious if you're already primed to see something strange. Then there's the other side. These folks say that after a certain point, stacking up this many coincidences just doesn't hold water. Sure, you can explain away each odd detail if you pile on enough special cases. A weird interior, perfectly distributed ice, lucky spins, a miraculous course correction. Eventually, you're just stretching. Occam's razor tells us to go with the simple answer, but what if the simple answer is exactly what it looks like? What if something really is steering this thing right toward Jupiter's Hill radius, and the pattern isn't a fluke at all? Polarimetric data has thrown a whole new twist into this debate. When researchers looked at how 3IATLAS scatters light, they found a negative polarization branch, deeper and narrower than anything we've ever seen from a comet or asteroid. Polarization tells us a lot about an object's surface and the particles around it, and in this case, 3IATLAS just doesn't match anything else we know in the solar system. That's not a guess. That's what the numbers say. Something about its surface or coma is genuinely different from every object we've cataloged so far. The safe, textbook answer is that its composition or the size of its particles is odd because it formed somewhere else, around another star, under totally different conditions. The wilder possibility is that we're looking at material or structures that don't even form naturally. Nobody can say for sure which explanation is right. That's what's driving everyone nuts. We're bumping up against the limits of what our tools can tell us. We know its path is bizarre. Our measurements are good enough to be sure of that. But we can't measure well enough to say anything about intent or artificiality. We spot this weird polarimetric signature, but we can't just send a probe to grab a sample. We watched it accelerate at perihelion, but there's no way to rewind the clock and do it all over again with better gear. We're stuck with a few snapshots when what we really need is a full movie. And time running out. 3IATLAS is moving away from the sun, heading for Jupiter's Hill radius and fatting fast. Every day it's dimmer, drifting farther from Earth and the Sun. The window for observations is closing. By early 2026, unless you've got access to the biggest telescopes on the planet, you're probably out of luck. If we want answers, if we want data that can settle this debate instead of just fueling more arguments, we have to act now while we can still see it clearly. Teams are scrambling. Ground-based telescopes with adaptive optics are trying to resolve the nucleus directly, get us actual size and shape, not just guesses based on brightness or coma. Other groups are collecting data across the spectrum: optical, infrared, ultraviolet, even radar if the angle and signal strength work out. Every part of the spectrum gives us something unique. Optical shows structure and dust. Infrared digs into which gases or ices are present. Ultraviolet can spot volatile emissions. Radio could tell us about heat or surface features. The main thing everyone's watching is the non-gravitational acceleration. If 3IATLAS keeps accelerating in a steady, specific direction as it heads for the Hill radius, that means something. Normal outgassing from a comet should make its speed wobble around. Different parts heat up, ice burns off. The comet gets closer or farther from the Sun. Constant acceleration in just one direction. That's suspicious. That would hint at something more than just random jets of gas. Spectroscopic teams are also on high alert, looking for weird emission or absorption lines, anything that points to unexpected materials. Comets usually turn up water, CO2, dust, the usual stuff. If 3IATLAS starts giving off signals from metals, refractory materials that shouldn't be vaporizing at these temperatures, or man-made compounds, then we've got a real mystery. So far, nothing like that has turned up, but people are still looking while it's visible. And then there's the big question. What happens when 3IATLAS finally hits Jupiter's Hill radius? Does it just keep cruising, another interstellar object passing through? Or does something dramatic happen? A breakup, a flash, some sign that crossing this gravitational line triggers a reaction? If the Sentinel idea has any truth to it, maybe we'll see something wild at that point. If it's just a weird natural comet, then nothing will happen. It'll just keep on fatting, heading out into deep space, and that'll be the end of the story. Looks like the Hill radius encounter is coming up sometime between mid and late 2026. The timing depends on some tweaks to the trajectory, which will get clearer as more observations come in. That gives us about a year, 1 year to track, to collect data, to just watch this thing and try to figure out what it actually is. For astronomers, it's a mix of excitement and exasperation. On the one hand, we get to watch something genuinely weird unfold in real time, using instruments that can spot details we couldn't have dreamed of a decade ago. On the other, even with all this shiny tech, we're still left squinting through a haze of uncertainty. There are different theories, and none of them can be nailed down for sure without a much closer look than we can get right now. A few research teams have quietly floated ideas for missions, spacecraft concepts that might intercept 3IATLAS, or at least get close enough for high-res pictures and maybe take some direct measurements. But let's be real, intercepting something from another star is insanely hard. This thing is moving fast, and its path doesn't line up with anything else in our system. To catch it, you'd need a rocket with an absurd amount of fuel and velocity change, delta V, as the engineers call it. Even if you could launch a probe tomorrow, which you can't because spacecraft take years to build, you'd be lucky to get to it before it slips out of range. Just look at New Horizons. It's flying away from the Sun at about 14 kilometers per second, blazing fast for a spacecraft. Still took it nearly 10 years to reach Pluto. 3IATLAS is moving even faster, and not in a direction that helps us. An intercept mission would need to be faster still, and honestly, with what we've got now, it's just not possible unless you want to wait decades for some ion drive probe to catch up. By the time anything reached it, the object would probably be past Jupiter, already too far for the kind of close-up observations that would answer our questions. So, we're stuck observing from afar. All we can do is collect photons, radio signals, whatever else we can grab, and try to piece together the truth from a handful of clues. It's like looking at a car from a mile away with binoculars. Sure, you can see it's a car. Maybe you can guess its size and how fast it's moving, but you can't read the license plate. You can't see who's behind the wheel. You don't know if it's a self-driving car or someone just wandering the back roads. And the bigger picture. It goes way beyond this one weird visitor. If 3IATLAS turns out to be natural, just a comet with a freakishly wild path, then it's teaching us the universe can throw out coincidences so bizarre, they mess with our sense of what's random and what's by design. That's honestly valuable. It's a reminder not to leap to conclusions, to stay sharp, and to accept that sometimes nature just looks like it was planned, even when it was. But if it isn't natural, if it's some kind of probe, a piece of tech from another civilization, that changes everything. It means we're not alone. Someone else is out there, traveling between stars, sending hardware into our solar system, pulling off trajectories we're only starting to figure out ourselves. Maybe our whole idea of how rare advanced civilizations are is just wrong. Maybe the answer to the Fermi paradox, where is everybody, isn't nowhere. Maybe it's closer than you'd think. And if that's true, we have to rethink first contact completely. We always picture it as this dramatic moment, a radio signal, a ship in orbit, alien ambassadors. But what if that's not how it goes? What if first contact is a slow process, something that's been happening right under our noses for years, maybe centuries? What if they've been here, watching from a safe distance, and we're only just now developing the tools to spot the faint outlines of their presence? That idea is wild and a little bit scary. Sure, it's exciting, finally we'd have an answer to the old question, are we alone? But then you realize what that answer means. Someone or something has been watching us, studying us, taking notes maybe, and not bothering to say hello. Suddenly, we're the lab rats, and we never even agreed to the experiment. Whoever's out there, their motives are a black box to us. We can't even guess what they want or how they go about their work. And honestly, this rabbit hole just keeps getting deeper. If advanced civilizations actually use these sentinel networks to keep tabs on star systems, Earth's probably been under the microscope for way longer than just the few months since 3IATLAS showed up. There could already be probes here, maybe tucked away in the asteroid belt, blending in with the space rocks we haven't named yet. Or maybe they're sitting perfectly still at Earth-Sun Lagrange points, those cosmic parking spots where you can hang out forever. For all we know, they're already sending back reports about us, and someone, or something, light years away is reading them and deciding what comes next. The more you think about it, the more the whole plan makes sense. If you can cross the stars, you don't want to send actual people everywhere. That's risky and expensive. You'd send machines. Cheap, tough, self-sufficient machines that can last for ages without help. You scatter them across the galaxy like dandelion seeds, let them orbit interesting stars, and wait for the data to roll in. Over millions of years, you build a map, see which places are worth a closer look, which ones grow life, which ones start building radios and rockets. From that angle, maybe we're just a line in a spreadsheet that stretches across the galaxy. Nothing special, not the center of the story, just another sample. And whoever's watching, they might not care about our politics, our history, any of it. They're just logging the facts like we do with bacteria under a microscope. Interesting to note, sure, but not exactly stirring the soul. That's a tough pill to swallow. For a lot of people, it actually feels worse than the idea of alien invaders. At least if someone wants to invade, they're admitting we matter. We're on the board, we count, even if only as a threat. But if we're just background noise to some cosmic survey, if we're nothing but an entry in a database, that stings. Still, maybe that's the reality. 3IATLAS isn't paying attention to us at all. It's locked in on Jupiter, following its own agenda, and we're not even a footnote. The biggest thing happening in our solar system might have nothing to do with us. We're just here, going about our business, wrapped up in our own stories, while something far bigger plays out overhead, and whoever's behind it doesn't even notice us. As 3IATLAS keeps moving toward Jupiter's Hill radius over the next few months, we'll gather more data, sharper images, better math. Maybe we'll finally see something that gives us a clear answer. Or maybe it'll just get messier, more open to debate, more fuel for arguments. That's science for you. Neat answers are rare. Most of the time, you get a tangle of evidence that points in every direction, and you just have to sit with the uncertainty until something breaks. But here's what we do know. Something is moving through our solar system, and it doesn't fit the usual patterns. It's headed somewhere that makes sense if you want to watch from a distance, and it's moving with a kind of precision that's hard to chalk up to random chance. Whether it's a comet or something stranger, it's making us face questions about our place in the universe, questions we're not exactly eager to answer. Are we alone in the universe? Probably not. Is anyone out there actually noticing us? Honestly, it doesn't look like it. And as for whether we matter in the grand scheme of things, well, the jury's still out, but so far, the evidence isn't helping our case. 3IATLAS is a reminder to stay humble. It's proof that Earth isn't the center of anything, and our solar system is just another face in a cosmic crowd. If someone or something is exploring the galaxy, odds are we don't even make the list of interesting stops. Yet, 3IATLAS is also showing us that precision and intention can show up where we least expect them. Maybe that's because of natural processes we barely understand, or maybe it's something engineered that's totally outside our experience. Either way, the effect is the same. We're watching something unfold that's way beyond our control and honestly, almost out of reach for our understanding. We're just witnesses, trying to make sense of events shaped by forces, or minds, that work on scales we can barely imagine. Remember how ancient philosophers talked about the music of the spheres? This idea that planets and stars make harmonies as they move. Sure, that's not literally true, but there's something there. Maybe there are real patterns and purposes stitched into the dance of things through space, rhythms and paths that hint at deeper truths than we've dared to guess. Maybe 3IATLAS is a note in that cosmic song, and we're just now learning to listen. Or maybe it's just a comet, just a hunk of ice and rock from another star system, shaped by randomness, nudged across the galaxy for millions of years, finally ending up here, and we happen to spot it because our technology is finally up to the job. Maybe all the weirdness and apparent purpose we see is just our brains, desperate to find meaning, connecting dots that don't really connect. But even if that's all it is, even if 3IATLAS is nothing but a natural wanderer, it's still teaching us something big. The universe is stranger than we thought. These visitors from other star systems bring with them evidence of different chemistries, different origins, whole histories we've never seen before. Our neat little models based on our own solar system turn out to be local guesses, not universal rules. When we try to use them on something truly alien, they just don't fit. And it's a reminder that our galaxy is full of mysteries we haven't even started to crack. Every point of light in the night sky could be sending out objects like this. Every star is a possible source for comets and asteroids, some of which end up drifting into our part of space. Only now are we getting the tools to spot these visitors when they show up. 100 years ago, 3IATLAS would have slipped by unnoticed. 100 years from now, we might be tracking dozens at once, finally building a real picture of what's out there between the stars. That's where we're headed. We're living in the moment when humanity goes from only knowing its own backyard to peering beyond it, seeing and studying objects from other worlds. We're the ones who get to make first contact with interstellar material, even if it's just frozen rock and ice. Or maybe not just that, maybe something more. Something that turns our ideas about exploration and intelligence, maybe even about life itself, upside down. In the next few months, we'll learn more. Observations will pile up. Scientists will argue, run new simulations, publish papers, debate every little detail. Amateur astronomers will keep scanning the sky, catching things that might surprise even the experts. And through it all, 3IATLAS will keep moving, right on schedule, heading for its close encounter with Jupiter's gravity. But let's not lose sight of how wild this really is. In all the centuries humans have watched the heavens, going back to the earliest sky watchers, we've never seen anything quite like this. Ancient people stared at comets with a mix of fear and wonder, thinking they were omens, signs from the gods. They didn't know where these objects came from or where they were going. For them, comets were magical, unpredictable visitors, not physical objects obeying the laws of physics. The scientific revolution flipped our whole view of comets. Newton came along with his laws of motion and gravity, and suddenly comets weren't omens from the gods. They were just icy rocks, following regular, predictable paths around the sun. Edmund Halley did the math and showed that some comets make repeat visits, proving they belong here, just like the planets. By the time the 19th and 20th centuries rolled around, we'd cataloged hundreds of them. We knew they were mostly ice and rock, and we'd built up solid models that explained exactly what happens when they swing in close to the sun and then drift way back out. But here's the thing. All our knowledge, all those years of peering through telescopes and scribbling equations, was built from studying our own local family. Every comet we looked at was born from the same ancient cloud of dust and gas that made the sun and planets. They all shared the same chemistry, the same origin story. Our models worked because, deep down, we were looking at variations on the same theme. Then in 2017, everything changed with Oumuamua. For the first time, we'd caught something that unmistakably came from outside the solar system. Its path wasn't bound to the sun, it just flew straight through, a true interstellar visitor. The excitement was off the charts. Suddenly, we had a piece of another star system passing through our backyard. We could finally compare our familiar comets to something truly alien. But Oumuamua was weirder than anyone expected. It was long and skinny, about 10 times longer than it was wide, which didn't fit anything we knew. Its surface was strangely reflective, not matching any comet or asteroid in our catalog. And the weirdest part, it sped up as it left the sun, but without the usual jets of gas and dust we see in comets. Scientists scrambled for explanations. Maybe it was a hydrogen iceberg or a chunk of nitrogen ice, or, and this was the wildest idea, maybe even something artificial. Avi Loeb at Harvard tossed out the possibility that it could be alien technology, like a light sail or a piece of debris. Most folks rolled their eyes at that, but still. It cracked open a door that had stayed firmly shut for decades. Fast forward to 2019, and along comes 2I/Borisov. This one looked and acted exactly like a comet should. It had a bright coma, a tail, water ice, carbon monoxide, everything checked out. Borisov reassured everyone. Most interstellar visitors are probably just regular comets, flung out of their home systems, drifting through the galaxy until they cross our path. The universe made sense again. We could all relax. But then came 3IATLAS. At first it seemed normal coma, outgassing all the right signs. Just another interstellar comet, right? But as the data piled up, the oddities started to stack. Its path was too perfect. The way it approached Jupiter's zone of influence was almost creepily exact. Even its acceleration near the sun happened at just the right moment in just the right direction to steer its journey even closer. The coma was unnaturally symmetrical. Its polarimetric fingerprint didn't match anything we'd seen before. You could explain away any one of these weird details if you tried hard enough, but all of them together in one object. That's when the arguments start. Astronomers split into factions, scientific papers start hedging their bets, and nobody wants to be the one who missed something obvious, or the one who went out on a limb with a wild claim. The observation campaign for 3IATLAS has been non-stop. From the day astronomers first spotted it, July 1st, 2025, this chunk of rock and ice basically became a celebrity in the solar system. The Atlas survey didn't waste a second. As soon as they realized what they'd found, they sent out alerts to observatories all over the world. Within hours, dozens of telescopes were already tracking this interstellar traveler. Within days, astronomers were scrambling to submit observation proposals to every major facility that had the right tools for the job. Even the Hubble Space Telescope, which usually gets booked up years in advance, shuffled its schedule to squeeze in a look. And James Webb, the most powerful infrared observatory we've ever built, set aside precious time for a deep dive into the comet's coma and nucleus, grabbing spectroscopic data nobody wanted to miss. All over the planet, ground-based observatories teamed up. They planned things so there'd always be someone watching as the Earth spun. As the sun rose in Chilean telescopes there had to close, scopes in Hawaii were just getting started. By the time Hawaii wrapped up, the Canary Islands picked up the baton. It turned into a round-the-clock relay, each observatory collecting data during its window and handing off to the next. Even amateur astronomers jumped in, adding their own observations from hundreds of smaller telescopes. Sure, they didn't have the firepower of the big observatories, but they offered extra data points, fresh perspectives, and sometimes even confirmed weird features the pros had spotted. As the weeks ticked by, the flood of data gave us a sharper picture of 3IATLAS, and a stranger one too. High-ray spectroscopy confirmed the odd carbon dioxide dominance we talked about before, but it also turned up traces of stranger stuff. Organic molecules, complex carbon chains, all hinting at wild chemistry happening in the coma as sunlight smashed apart simple molecules and let them recombine in surprising ways. That's nothing new for comets. But the mix of molecules and their relative amounts just didn't line up with what our models predicted for something with 3IATLAS's ingredients and temperature. And then there was the brightness. Careful tracking of how the comet's light changed over time showed clear periodic swings, signs the nucleus was spinning. But pinning down the exact rotation period, not so simple. Different analysis methods spat out numbers anywhere from about 8 to almost 12 hours for a full spin. That uncertainty is a headache, because the comet's rotation changes everything about how it vents gas. A fast spinner heats up and cools down differently than a slow one, and different parts of the surface get blasted by sunlight at different times, making the outgassing jets shoot off in unpredictable directions. The coma and tail changed too, in ways that were half expected and half baffling. As 3IATLAS got closer to the sun, solar heating cranked up, and the coma ballooned and brightened, just what you'd expect. But it grew faster than you'd see with a typical water ice comet, yet not as fast as a pure carbon dioxide-driven one. The tail, that classic comet feature stretching behind it, looked wild in close-up images. There were multiple streamers, uneven brightness, even weird knots or blobs drifting along at different speeds. Some scientists started thinking these might come from sudden outbursts, brief but violent eruptions when hidden pockets of volatile ice suddenly hit sunlight and vented in a rush. That happens with comets sometimes. Heat seeps in, reaches a layer of especially touchy ice, and boom, eruption. But with 3IATLAS, the timing and frequency of these outbursts just didn't fit the models. They popped up more regularly than you'd expect if the process was really just random heat reaching buried ice in a chaotic interior. So, the mystery only deepened. Now here's the tricky part, what we're not seeing. Astronomers tried to pick up radio signals from the nucleus itself, hopping for some thermal radiation from sunlight hitting the surface. That kind of data could have told us a lot about temperature and what the comet's made of. But 3IATLAS barely registered in the radio wavelengths. It came in fainter than anyone expected for something its size and distance, which threw everyone off. Maybe the nucleus is just smaller than we thought. Maybe its surface doesn't radiate heat the way most comets do. Or maybe, and this is kind of wild, something about the texture or composition of the surface scatters radio waves in ways we didn't expect. They also tried radar, blasting strong radio signals at the comet and listening for echoes. Mostly, no luck. The thing was too far, probably too small, and most radar setups just couldn't pick up anything useful. Arecibo might have had a shot, but it collapsed in 2020, which still stings. Goldstone and a few other places tried anyway, but came up empty. There were a couple of maybe detections, just faint signals that could have been echoes or could have been static. Nothing anyone could pin down. Then, as October 2025 rolled around and perihelion got close, the excitement in the astronomy world hit a fever pitch. This was the big moment, the comet's closest approach to the sun. That's when comets get wild, more active, brighter, and sometimes they just don't make it. The sun's heat, the violent jets of gas, the tidal forces, any of those could tear a comet apart. If 3IATLAS was going to break up, this was when it would happen. But as luck would have it, perihelion lined up with solar conjunction from Earth's point of view. The comet was tucked behind the sun, totally out of sight. For a crucial 40 to 60 hours, nobody on Earth could see a thing. A few spacecraft in the right spots, like Starry ahead of Earth in its orbit and Soho parked between Earth and the sun, kept watching. They caught some good data, but their instruments weren't really built for this kind of comet work. They could track brightness and spot big changes, but not the fine details. No high-res images, no detailed spectra. When 3IATLAS finally reappeared, every astronomer watching had the same question: did it survive? First images said yes. The nucleus was still together. The coma looked bigger and brighter, which made sense, and nobody saw any signs of a breakup. Relief for sure, but also a new wave of curiosity. The comet made it through, so what did that say about its structure, its insides? But what else had changed? That's when things got weird. Astronomers spotted an acceleration anomaly. The comet's path after perihelion didn't quite line up with the models from before. Something nudged it, changed its speed and direction just enough that gravity alone couldn't explain it. The effect was tiny, fractions of a millimeter per second squared. But it was there, and it pointed almost exactly where you'd want if you were aiming for Jupiter's Hill radius. The reaction in the scientific community was immediate and honestly a bit chaotic. Papers flew back and forth. Some argued for natural causes, others pushed back. Arguments broke out at conferences, in journal reviews, on astronomy email lists. Anywhere people could debate how to model comet outgassing, how to trust different observation techniques, all of it. The thing is, both sides had a case. People arguing for a natural explanation had a ton of comet history to back them up. Non-gravitational accelerations happen all the time, and there are records of plenty of comets acting this way. They could point out that humans love to see patterns, even when it's just noise. And maybe, they said, that's what was happening here. A lot of excitement over something that's just part of the usual comet weirdness. People who pushed for alternative explanations loved pointing out the weird little details that didn't fit the usual models. Like, how did it pull off such a precise trajectory? Why did it speed up exactly when it did? And why did the coma stay so uniform, even though the outgassing should have been strong enough to mess with its orbit? They'd say, look, sometimes the obvious answer is the right one. If an object moves like it's being guided, maybe that's because it is. But honestly, beneath all the back-and-forth debates, there was something that most professional astronomers just refused to say out loud. The possibility that 3IATLAS wasn't natural at all. Maybe it was artificial, a probe, a spacecraft, or some kind of explorer sent by another civilization. That idea wasn't new. Scientists had been tossing around the concept of interstellar probes for decades. Von Neumann probes, those self-replicating robots that could explore the galaxy on their own, show up all the time in theoretical papers. SETI folks have written loads about how to spot signs of alien tech in space, but actually standing up and saying, hey, maybe this thing we're looking at is artificial, that's risky. You could tank your career with one sentence. The scientific community has a strong allergy to hype. If you make a big claim without rock-solid evidence, good luck getting your paper published, or your next grant approved, or your reputation back. Even if you're right, you have to prove it beyond all reasonable doubt. And the more extraordinary your claim, the higher that bar gets. So most astronomers who even wondered deep down if 3IATLAS might be more than a comet kept those thoughts to themselves. Publicly, they stuck to safe phrases like unusual properties and unexpected behaviors, never daring to talk openly about artificial origins. Meanwhile, outside academia, the rumor mill spun up to full speed. Social media ate it up. YouTube filled with videos breaking down every frame of every observation, racking up millions of views. Amateurs scoured public data, looking for clues the pros might have missed or ignored on purpose, depending who you asked. Some of these people knew their stuff. They genuinely wanted to help. Others just spun wild theories, some bordering on conspiracy. Most fell somewhere in the middle, mixing smart questions with leaps of logic. Then the amateur astronomers jumped in with their own images, and things got even wilder. Paul Craig's wasn't alone. Plenty of backyard astrophotographers, using gear you can buy online, claim they saw structures in 3IATLAS that you couldn't spot in the official Hubble or James Webb photos. Maybe that sounds sketchy, but there are real technical reasons this happens. Amateurs use different cameras, different filters, and their image processing is all over the place. Sometimes they pick up certain wavelengths better. Sometimes their processing just adds fake details that aren't really there. So now, everyone argued about what to do with these amateur observations. Should they count as real data? Should we ignore them as probably flawed? Or treat them as maybe useful as long as we double-check? Scientists couldn't agree. Some said science is for everyone. If you've got the tools and know-how, your data matters. Others insisted only pros with finely tuned equipment could be trusted. But no one argued about one thing. 3IATLAS grabbed the public's attention in a way most space stuff just does. Timing had a lot to do with it. These days, we take the idea of alien life and intelligence way more seriously than we used to. Governments now admit to UAP sightings, which would have been laughed off not long ago. We've found thousands of exoplanets, so we know planets are everywhere. Suddenly, other civilizations don't seem so far-fetched, and technology's racing ahead. AI, robotics, new ways to explore space. The thought of autonomous probes from another star doesn't seem crazy anymore. It just sounds like a tough engineering problem waiting to be solved. With everything we've believed about life beyond Earth, it's no wonder an interstellar object acting strangely feels like more than a footnote in some science journal. It hits something deep, old questions we've carried forever. Are we really alone? Did someone notice us? Are they already here? These aren't just late-night debates anymore. They're real questions with answers possibly barreling toward us, ready or not, and 3IATLAS might have those answers. When 3IATLAS showed up, you could see the tug-of-war play out in the news. Scientists kept things buttoned up, unusual comet, some oddities, nothing conclusive yet. But online, in the comments on social media, in all those wild corners of the internet, theories exploded. People talked about government secrets, hidden data, scientists whispering behind closed doors. Some of it was pure paranoia. Some of it was just people wondering if we're really getting the whole truth. Here's the part nobody likes to admit. We aren't getting the whole story. Not because someone's hiding it, but because the story's still being written. The data's raw. Nobody agrees on what it means yet. Every new observation tweaks the math, changes the trajectory, stirs up fresh arguments. We're watching science as it happens, messy, incomplete, and full of ideas that might get tossed out tomorrow. That tidy, satisfying version where everything fits together, that's years away. Right now we're stuck with the uncertainty, but eventually this limbo ends. 3IATLAS is out there, about 14 or 15 times the Earth's distance from the Sun, on its way toward Jupiter. Each day it gets closer to something big. The moment it crosses into Jupiter's Hill radius, that's when things get interesting. If you're counting, we'll hit that point somewhere in mid to late 2026, just 10 or 12 months from now. In cosmic terms, that's nothing, and it's not a moving target. Unlike so many questions in science, this one's got a ticking clock. Teams are already getting ready. They're lining up telescopes, planning round-the-clock coverage. High-res cameras will look for anything weird, breakups, shape changes, anything suspicious. Spectroscopy will check for odd chemicals or emissions. Photometers will watch for flickers in brightness. Radio telescopes will listen for signals or heat. Even radar's getting in on it, trying to ping the object for a close-up sense of its structure. If 3IATLAS is just a comet, it'll cross Jupiter's Hill radius, get nudged a little by gravity, and drift off into the dark. Outgassing will taper as it moves away from the Sun. The coma and tail will fade. Soon it'll be too faint to spot, just another lost traveler between the stars. But if it's something else, if there's more going on, then the Hill crossing could blow the whole thing open. A breakup that isn't chaotic but looks coordinated. That's suspicious. A sudden course change that gravity or outgassing can't explain. That's huge. Strange heat, weird bursts of light, signs of machinery or systems at work, those would be wild. And if we pick up any kind of signal, something ordered that nature just doesn't do, that would be the moment we know. Scientists are gearing up for just about anything right now, even though honestly most expect nothing dramatic to happen. Comet swings by, nothing weird, everyone heads home. That's probably the smart money. Nature usually doesn't match our wildest hopes. Still, people are getting ready for the unexpected. There are plans in place in case something truly strange pops up. Not always official government playbooks, though you never know what's buried in classified files, but loose networks of researchers who know how to get the word out, double-check a discovery, and avoid jumping at shadows without missing something big. But what happens after? Let's say 3IATLAS shows up, does nothing but act like a weird comet, and then disappears. What do we do with all the questions it stirred up? Do we just chalk it up as a curiosity and forget about it? Or do we use this whole episode to push for better ways to spot and study things that might not be natural? Some scientists aren't waiting to find out. They're pushing for better sky surveys, hoping to catch these interstellar visitors earlier, while they're still far out and we have more time to get ready. More lead time means more data, more chances to really look before they're gone for good. There are ideas floating around for telescopes built just to spot faint, quick-moving things, and for new models that can give us a sharper sense of what a normal comet should do, so we can spot the outliers. Others want rapid response spacecraft ready to launch in a hurry and actually meet these objects up close. Of course, all this takes money. Political will and a lot of patience, years, maybe decades. It's easy to write up a proposal, much harder to make it all happen, but maybe 3IATLAS is the kick we need. At the very least, it's made it clear that we're just barely keeping up with these interstellar surprises, and that the payoff for getting better at this could be huge. Really, that's the big picture. It's not just about one oddball comet, it's about what it means for us going forward. We're starting to look past our own backyard. We're building tools to spot and study messengers from other star systems. We're circling around the old question, are we alone, or is someone else out there, sending their own probes, poking around the galaxy just like us? Maybe 3IATLAS has the answers. Maybe it just stirs up more mysteries. Science works like that. Either way, it's a reminder. The universe is stranger and deeper than we ever guessed. It's a lesson in humility, showing us how much we still don't know, and a glimpse of what's coming when spotting interstellar objects becomes routine, when we can finally say with confidence what's natural and what isn't, and when we're ready to face whatever we find. When 3IATLAS reaches that edge, crosses into the hill radius, and either sails through or throws us a curveball, we'll get our answer, or at least part of one. Even if it's just a weird but natural comet, even if every oddity gets cleared up with better data, the questions it leaves behind won't just fade away. The possibilities it hinted at will stick with us. We'll remember that order can come out of chaos, that nature sometimes fakes design, and that our search for meaning is always limited by the tools we have and the stories we're willing to imagine. If it turns out we're dealing with something artificial, if all those months of watching reveal signs of someone steering this thing or evidence of a deliberate design, then everything flips. That silence out there, the one that's bothered scientists for ages because we never hear alien signals, there's your answer. They're not sending out messages. They're just watching. They're here, right in our solar system, hanging around long enough to set up shop in ways we're only just starting to notice. Either way, the consequences are huge. If 3IATLAS is natural, we're looking at a universe that can cough up events so weird and unlikely, they almost look like someone planned them. That tells us our current ways of telling, designed from natural, just aren't good enough. We need sharper tools, methods that can actually separate strange but possible from so strange it demands another explanation. We need a dose of humility too, because spotting purpose in complicated things isn't something humans do well, especially when we're out of our depth. Honestly, even with human stuff, proving intent is tough. Archaeologists argue about whether ancient stones are ruins or just rocks. Cryptographers try to tell codes from random static. We're wired to see patterns, sometimes too well. We find faces in clouds, animals in stars, meaning in pure coincidence. Now imagine trying to do that at a cosmic scale with objects from other solar systems and no idea what normal even looks like. The challenge just gets mind-boggling. But if 3IATLAS is artificial, that's a whole different story. Suddenly the Fermi paradox, the big where is everybody, has an answer, and it's a little unsettling. They're not far away. They're here. They've been here. They're watching us, not from distant galaxies, but from the same orbital zones we're only now learning to search. First contact isn't some future event we're waiting for. It's already happening and we're just starting to catch on. So what do we do if we confirm it's artificial? What if we prove, no question, that it's a probe or some kind of carrier craft? Do we try to talk to it? Chase after it with our own spacecraft? Or do we just watch and take notes, treating it like a rare animal we don't want to disturb? These aren't just technical problems. They're political, philosophical, and maybe even spiritual questions about whether we're really ready to meet something non-human on its terms, not ours. There's this idea in the whole contact discussion called the Great Filter. It's the theory that somewhere between basic chemistry and galaxy-spanning societies, there's a wall most life never gets past. Maybe it's life starting in the first place. Maybe it's getting smart enough. Maybe it's surviving your own technology. Or maybe it's something even further down the road, something we can't even imagine yet. If 3IATLAS is proof of a civilization that's solved interstellar travel, built networks to watch other star systems, and survived long enough to set all this up, then they've already jumped hurdles we haven't even reached. They've solved problems we're still struggling with. They've made it through challenges that might still be waiting for us. So what does that mean for our own future? Are they a goal to aim for, proof that a technological civilization can last? Or are they a warning, showing that survival demands choices and sacrifices we might not like? This brings us to values, and that's where things really get tricky. If the galaxy is full of sentinel networks, automated watchers keeping tabs on young civilizations, what does that say about the ethics of whoever built them? Is watching without consent just neutral science, like how we track animals here on Earth? Or is it surveillance, a massive breach of privacy and autonomy, but on a galactic scale? We can't answer that without knowing their intent, and unless we actually talk to them, we're stuck guessing. Don't forget the time factor here. If 3IATLAS is artificial, how old is it really? Maybe it launched just a few hundred or thousand years ago, recent, at least on a cosmic scale, from a civilization that's still out there, growing, changing. Or maybe it's ancient, something left behind by beings who vanished ages ago, still following commands from programmers who have long since turned to dust. Machines can easily outlast their makers. Look at Voyager. Those probes will keep drifting through space for millions of years, long after humanity's story might be over, still carrying our message as they go. If we're dealing with probes from civilizations that are already extinct, then contact takes on a different meaning. We're not meeting another mind, we're discovering a relic. It's not a conversation, it's more like finding a message in a bottle tossed into the cosmic ocean eons ago. Honestly, that idea is both less scary and a little sad. Less scary because there's no one on the other end, no motives to worry about, no misunderstandings or threats. But sadder too, because it hints that even star-faring civilizations don't last forever. That space might be filled with the ghosts and debris of species that reached out before fading away. Humans have been wrestling with the idea of contact for ages, ever since we first realized we might not be alone. Science fictions run wild with the possibilities. Friendly galactic clubs, hostile empires, weird machine minds that barely notice us. But stories are one thing. Actually facing non-human intelligence, even if it's just a lone probe, is something we've never done. Who knows how it would hit us? Would it shake up our religions, our politics, our self-image? Do we rally together, or do we split into camps, each with its own spin and agenda? History doesn't offer a clear answer. Big changes sometimes pull people together, like when the Apollo program made us feel like one species staring at the moon. But just as often, they drive us apart. The scientific revolution, the industrial revolution, the internet, all of them sparked fights between people who wanted change and people who wanted things to stay the same. Meeting non-human intelligence, that would make all those shifts look small. And are we even ready for this? as a species, not just as scientists. Some folks would embrace it. Others would insist it's fake, no matter what evidence you show them. For some, it'd be proof of beliefs they've clung to for years. For others, it might feel like a threat to everything they thought was true. The reactions would be all over the map because, well, so are people. That's why scientists have been so careful about how they talk about 3IATLAS possibly being artificial. It's not just about avoiding embarrassment if they're wrong. It's about responsibility. Announcing something that could change how billions of people see their place in the universe isn't a small thing. If they screw up, cry alien over what turns out to be a comet, people lose trust, not just in them but in science as a whole. But if they're too cautious and ignore real evidence, that's its own failure. Science only works if you follow the truth, even when it's weird or uncomfortable. The next year is going to be a test, as more data comes in. As we get a better sense of where 3IATLAS is headed, scientists will have some tough calls to make. Wait too long to say anything and people might accuse them of hiding the truth. Say something too soon and they could cause panic over nothing. There's no perfect playbook. They'll have to walk a tightrope between skepticism and curiosity, between protecting society and pushing for answers. And all the while, 3IATLAS just keeps going. If it's natural, it's totally oblivious, doesn't care about our fuss, our telescopes, our debates. If it's artificial, maybe it knows we're watching, maybe it was even built to notice us or to avoid us. But it's not reacting. It just keeps moving, steady as ever, toward wherever it's supposed to go. Out in the freezing emptiness between Saturn and Uranus, something strange is happening. There's a visitor from another star drifting through our solar system. Maybe it's about to pull off the biggest move in human history. Or maybe it's just coasting along, doing what space rocks have always done, obeying gravity, riding momentum, not aiming anywhere at all. Honestly, nobody knows yet. But we're watching. We're tracking every twitch, every faint signal with all the technology we've got. Because this could be it. The moment everything changes. Maybe this is when humanity stops wondering if we're alone in the universe and finally gets an answer. Not a guess, not a theory, real evidence. The kind that makes you look up at the sky and feel in your bones that someone else is out there and they've come here. Or maybe not. Maybe we're about to learn that the universe is great at tricking us. Sometimes things line up in ways that look deliberate, but it's just random chaos falling into place for no reason at all. That's a lesson worth learning too. It's humbling, realizing the universe doesn't care about our expectations or what makes sense to us. Whichever way this goes, we're here for it. This is our generation's moment, these months, this shrinking window of time before the chance slips away. By this time next year, we'll know more. The Hill radius encounter will be behind us or happening right then. We'll have new data, maybe just more questions, maybe a real answer. And we'll be closer to figuring out what 3IATLAS really is, what it means for our place in the universe, and what it says about our future as a species reaching into the unknown. The clock's running, the gap's closing. Somewhere out there in the black between the worlds, this visitor is carrying questions and maybe answers that could flip everything we thought we understood. Are we ready? Not really. We never are. But ready or not, the moment's nearly here. When it comes, we'll finally know. Have we been tracking a comet or watching the first sign of intelligence that's been watching us for much longer than we've been watching it? 3IATLAS isn't slowing down. It never was. It's heading exactly where scientists hoped it wouldn't, right where the math said it had no business going, straight toward the spot you pick if you actually meant to be there. The universe is about to reveal if that's just luck or something more. And we're about to find out if we're alone or just one more curiosity in someone else's sky. The answer's on its way, whether we're ready or not.